It's a small group here, so it's uncertain whether we're going to get through this session in time. Yes, exactly. I was going to say, it's a small group here, so I encourage a lot of two-way discussion. Raise your hand, speak up whenever you have the opportunity. We have, okay, good. Okay, you have the slides open. We have speakers today from, ranging from the world of uncertainties. We'll start with Javier on the importance of uncertainties in forest monitoring and decision making. He's going to give us a perspective where we see uncertainties not as we usually do within confidence intervals and numbers and plus minus X, but more in how to make use of these uncertainties, how to understand them, and then how to use them in your decision-making processes. That will be followed by Robert Kennedy he's going to present an overarching framework on how to communicate uncertainty, how to tick all the boxes on the sources of uncertainty, and how to sort of summarize them to the general public in a consistent, coherent manner. And then we have Chad. Chad's going to dive in a little bit into the math. So you're going to see formulae and equations out there. He will present a number of methods to get to uncertainty in bias estimation, concluding on a method that is a geostatistical model. We'll have two country cases here. We're lucky enough to have the Republic of Sudan in the room with us, and Mexico. Don't see them, they know it already. So we'll have two quick cases on Mexico and Sudan as a part of that presentation. We'll have a hands-on then from Javier on the Monte Carlo tool to simplify uncertainty, and a presentation of the approach in Ghana for FCPF and trees. Okay, so without further ado, I'm going to pass on to Javier to get started.
Okay, well, thank you very much all for coming here. I hope that the technical hurdles are not too many. Okay, so I'm going to tell you next whenever we do next. It's very slow to connect from here. Yeah, I should. Maybe this one they can show it, because I don't know. Can you show instead this presentation? Because I don't know. Because in this computer is apparently it's very, very slow to connect. Okay. So thank you very much all for being here. This is an introductory presentation where, I mean, I have been working in uncertainties now for a little bit, and is it yours or no? Is this
This one, yeah.
Uncertain connection. Anyway, I have been working for a little bit with.
It goes in the spirit of uncertainty. It's coming.
So I'm gonna be I have been working a little bit for uncertainties, and talking to people in the government, talking to people in academia, and particularly because we are in the context of MRV in general, I have come to a personal appreciation that we have a very constrained view of what uncertainties are and how we can communicate it. And anyway, eventually in the end, whatever we do as technicians, it has to be translated at some point into decision making. So this talk is about how we can think slightly differently when we talk about uncertainties. Next. Yeah. Okay. Can you go next?
I think it's.
So it's very slow, everything.
No, it's not.
Okay. So it's still yours? Okay. Okay. So first I want to put you an example. And this is based on a poll done in 2020, where it was a survey among the public, where basically they were trying to see how uncertainties communicate to the general public and how the public perceive it. No? Because usually we have the feeling that decision makers, the policy makers, usually they want maximum reassurance. No, they don't like to talk about something in between two values. They want us to tell. They want you to tell them what is exactly the value that they want, right? However, someone did that poll, and it was a poll about communicated uncertainties on sea level rise. So it was a poll with 1,000 individuals, and 3 questions were asked to the public in that poll. In the first question, basically, the public were given a single, most likely prediction of sea level rise by year 2100. No, a single prediction. There was a second option where the public were given a most likely prediction, but augmented by an upper and lower bound. No, so you are starting to play with the typical concept of uncertainty that we work with. And then in the third one, much more complex, a most likely value, but then heard further information about a worst case scenario and also a statement of why it is not possible to foresee the full cause and consequences of sea level rise. Basically, the result was that people did not, as we would have expected, did not naively prefer the message expressed with no uncertainty. Actually, the second option, where you have an upper and lower bound confidence interval, was the one preferred by the public as in terms of appreciating how sea level rise, how probabilities of sea level rise were going to be likely in 2100. Okay, so that is the first, for me, unexpected result. Next. So we have basically we have the typical 2 options that we have with our result when we don't provide uncertainty to a decision maker. Okay, we just provide a single value, 0.6 in this case, 0.6 meters of sea level rise. Then we can provide the decision maker the most popular option in the previous poll, our central value with a sort of likely range. But then what I want to argue here today is that there is another way that might be potentially more informative to the decision maker. And in this way we are seeing uncertainty within the context of probabilities and risk. Usually decision makers, they like to bring this concept from a risk analysis perspective. So in this case, we can face a situation, for example, when we have a likely sea level rise, but then we have, for example, a threshold that might be like a target value where the decision maker says, okay, I really don't want to go beyond, for example, in this case, 0.8 meters of sea level rise. So the way you communicate uncertainty to that person, to that decision maker is, okay, you want a target value of 0.8. So then what I can give you is what is the probability that your sea level rise is going to be larger than the target value, which in this case is 0.16. No, it's this when you add up this area. In this case, 0.16. Okay, so now you are going from a pure confidence level where you can say when the decision maker will appreciate whether you are in or out, to a situation that is a more continuous, it's a probabilistic view. And when you tell the decision maker this, your probability that your target is going to be higher or lower than what you are expecting. Yeah. So the basic message here is we don't aim to reduce uncertainty to 0, which is always what we want. It's always the hurdle that we face. What we aim is to reduce the risk of taking a decision. The risk, when you do an action as a decision maker, what is the risk that you are going to face? The risk of being wrong, basically. Okay? Yes. So when we are talking in the concept of MRV, for example, we used to estimate uncertainties, no? Particularly for activity data, no? When we're reporting for emission factors, we can also report other uncertainties. These are just an example. It's not coming from any particular country. And we might have uncertainties that come from the combination of the different errors, no? What we call error propagation, etc. Today we know, and we will talk about it later, that countries are facing more and more the situation where they have to use Monte Carlo to produce this combination of errors. We'll talk about it later. Yeah. Okay. So again, just a reminder, it's basically the same slide as before. What we're aiming is to go from intervals to decision probabilities. Okay, and this is the same situation as before. We have a target. In this case, a slightly different target. And sorry, this is a target of 5 in this case. Okay, so we have an expected value. We have a target that the politicians want 5 to happen. This is the threshold value for the decision. And then in this case, we have a probability that our sea level rise is larger than 5 to be, in this case, 0.73. No? The same concept, just as a reminder. Based on these probabilities, potentially we can keep communicating to the decision maker in a simple way instead of communicating this continuous probability distribution. What we can do is a sort of a semaphore and a street light, a situation where we can tell them, okay, the probability of meeting your target is larger than 0.8. You can take an action that you stay, for example, in the business as usual, for example. You can do a red one where you say, okay, if your probability is 0.6, you can activate a plan B, no, of action, another different action. And you can do a number one in the middle that is, well, if you are between 0.6 and 0.8, your probability, you should be ready. You should launch contingency actions. Okay, and basically this is a sort of very simple risk rule where you are going to act on probability, not on point estimates. Okay. The next one is a little bit complicated, but you will see when they show the presentations. I don't want to go too deep into it. But the message here is because we are used to perceive that better precision is better. So when you have narrower confidence interval, let's say a narrower distribution is better. You are good. That is the objective that we aim with the IPCC. No, in principle, it is not mandatory. It is a recommended situation. Sandra is going to kill me later.
Minimize the uncertainty.
Minimize the uncertainty. Yeah. Okay. So that is the perception. We have to minimize the uncertainty. But when we are acting on this context with decision makers, there might be cases where not always minimizing the uncertainty might be the best action for a politician, for a decision maker. Okay? And here we have a simple model when we are incorporating an extra element. When we incorporate cost of taking action. Okay? So far we have not been dealing with cost. We only aim to reduce uncertainty. When you incorporate cost in the decision making, the picture might change. You might decide, I think this is a case where we are aiming to we have an action, business as usual, and we have another action where we, for example, increase the number of plots into NFI or whatever, increase the monitoring intensity in order to get a better precision. Now, the issue is, there might be cases where the cost of monitoring, of more intensifying more, is eventually larger in terms of probabilities, final probabilities, than the actual gain in precision. Okay, so marginal cost, exactly. Okay, so again, the message is sometimes better precision does not mean that the decision maker has to take an action. And I think this is a very important message, potentially, that you can pass to the decision maker. I have gone a little bit away from the pure MRV situations that we face. No? I'm trying to be a bit more general, but this is the basic concept. Thank you.
Javier,
So in essence, what we aim is to link actions to reducing decision risk based on uncertainty information. All right? That is the message. And decisions can also be transparent. We can inform the decision maker now not only about providing, like we usually do, like a central value and then a 95% confidence interval that we usually do. We can incorporate information on the decision probability, no? Like what we were saying before, the probability of meeting a certain target. We can inform the drivers of uncertainty. That is something contemplated in sensitivity analysis in Monte Carlo. No, when you say, okay, I have more uncertainty due to activity data, or due to emission factors, or due to deforestation, or due to degradation. We can pinpoint a little bit more on the drivers of uncertainty, and we can provide the street light rule, for example, as extra information. What is the next action according to the rules of the game, no, of the decision-making game that we are making? Okay.
Javier,
Yeah.
2 minutes.
2 minutes. Okay.
1 minute.
Yeah. Then finally, this is the last slide. There is a call to action on uncertainties that I want to make to countries. A possible recommendation, let's say, would be to adopt a simple risk rule, thresholds, these target thresholds, plus possible actions, and publish potentially probabilities for each estimate. For donors, please try to fund value of information positive improvements. No? Value of information is some of these elements that we have been talking about. And for example, adding more plots or improve emission factors or improve validation or fandom validation, whenever they should decisions, sorry. To agencies like the agency where I'm in FAO, we can try to standardize probability of meeting target outputs alongside the reporting of intervals. And for GFOI in particular, we could say, okay, maybe GFOI can provide examples, templates, and trainings for some sort of risk-based MRV that we are talking about. That's it. I just wanted to provide this sort of new message, at least, that I think might be for everyone. Thank you very much.
Thank you. Since we started slightly late, if you can hold your questions to the end, and then we should have 20, 30 minutes towards the end for a discussion. So we'll hand over straight to Robert Kennedy as soon as he's ready.
So you're driving, Chad? Okay. I waited until the very last moment to take off my jacket because it's so cold in here. Okay, well, let's see here. Is it still lagging? Not as bad. Okay, let's go ahead to the next one. So anyway, I'm Robert Kennedy. Nice to have you all here. Thank you for coming in the afternoon. I'm at Oregon State University, the little beaver on our logo, because we are a very forest-centric kind of university, so I'm super happy to be here. But what I'm going to talk about actually comes out of the NASA carbon monitoring system, and I was lead of what's called the Uncertainty Working Group. I consider myself a student of uncertainty, not necessarily an expert in uncertainty, but we recognize the need for it. And so we wanted to talk about sort of how we communicated it, findings of this working group. So let's go to the next one. Waiting, maybe we should, okay. So the first thing we learned, and this was the carbon monitoring system is a whole bunch of different disciplines focused around carbon. Atmospheric scientists, tree huggers, statisticians, everyone has their own sense internally, disciplinarily, about what uncertainty means. This is one definition, but what I like about it is this unachievable ideal of completely deterministic knowledge. So we know that we don't know everything, right? So let's go to the next one. And hit it one more time for both of the, there we go, both of the things, just fill that out. So you see this a lot. You see aleatoric and epistemic. Basically, some of the things that are uncertain in what we might produce are just because we can't avoid them because they're random effects. And then there are some things that we just don't know about our system. And so keeping that in mind is useful. But that's not really what we were interested in. Next one. So this is a backdrop, but the key thing is that it arises in different places when we're doing stuff, when we're producing knowledge, right? In our case, maybe producing maps or producing estimates, like Javier was just saying. So it has these components, there's different severities. Next, okay, keep going until this one fills out. But specifically when we're looking at maps, which we all do, I would make the argument that every time we're putting a label on a pixel, we're making a claim. Typically, let's keep going. I think you can just maybe just keep hitting them for a little bit here and just keep going. And you can keep going to the next slide and I'll catch up. How about that? Okay. So one thing is that you're making claims about places where you don't have reference data. So we talked about FI. This is a perfect example. You're making a biomass map. You're making a bunch of claims about biomass where you don't have observations, right? Keep going. Yep. And so when we had these discussions, we realized we really had to relax our disciplinary definition. So I urge you, as you're looking at this, to do that, please. We had to come up with ways to talk as a group and build this framework. Next. Let's skip over this. Too many words, given the time. But this is in the paper, which we're about to see. So the paper is a little hidden there, but it's an ERL paper from last year. The authors are from all these different disciplines, like I said. So really, I'm not going to try and tell you the whole paper in the next, 3 minutes that we've got. But I want to just tell you sort of the strategy behind it and sort of the key thing. But the idea was that it took us years of arguing to come up with this paper because we all had these different ideas of what uncertainty was. Chad is on this one, but as I said, there are lots of other folks. So this was one key piece, was we had to come up with what we considered a workflow that might apply to just about anything. We hoped that everyone reading the paper could see their own project in this workflow somehow, not necessarily every component. So this is one piece. I won't belabor it because I'm sure we could argue for the next hour and a half in this room about whether this is all right. But it is right, I promise, because we all argued about it for 2 years. So, but there's predictors, there's observations, and then predictions, and then there's a model involved. And if we go back to thinking about where the uncertainty comes from, this is really what we were trying to do. When we make a prediction, when we make that claim, we've got uncertainty coming in the generation of knowledge. We know that there are some places that we know that we don't know what's going on, but we don't have any choice. Maybe the data are not there. Maybe the computational capacity isn't there. We need to communicate when we are really not sure about what our uncertainty means. So we can make a claim about something. We can even make a claim about what the uncertainty is. We can come up with, we can even come up with those distributions, right? But if that distribution is only half of the things that we actually don't know about, then we've got a false claim in a way, right? So this is the communication part that we wanted to focus on. How much time do I have? 2 minutes? -7.
Yeah.
I'll just speak backwards.
Right.
Okay, I'll be as quick as I can. I don't know what's going on. Well, so when it comes back, so on the left-hand side are the different places where uncertainty can come into play. So we had the models, we had the sources, let's see, the predictors, the models, and the observations, and all of those have potential uncertainties, right? And the whole point of the, you can see it down there, the whole point of the framework is to be able to say, as a producer of knowledge, a map, let's say, right? I have an idea of what some of those things are that should be in my map. I have an idea of which things in my modeling process are not relevant, and I have an idea of which things are relevant and that I've done a good job with. And the point here is, I keep hearing myself. What are we doing? You want to mute it? This is very chaotic. Okay, so the point here is that this is a very simplistic. What's that? Okay. This is a very simplistic way of looking at things, not quite the red, green, yellow light thing, which was nice. But the idea is that we're going to, as a producer, your obligation should be to communicate what you don't know so that users taking your product can evaluate those claims. And if they see two different products that are different and the uncertainties don't match, if you don't give them warning that you don't expect them to match, they're just going to throw out everything, right? We know that. And so if we can say, my product, I take into account model structure and driver uncertainty, but I'm not messing with model parameters. So I would say model parameters are important, but I'm not going to mess with them. So when you look at my distribution of uncertainties coming out of my model, I'm not taking that into account. But there might be some things like sampling error with a design-based approach where you can say, yeah, that's what that's all about. So we can be very confident that that component of uncertainty is good. But if we're looking at validating disturbance maps with interpretation of planet data, anyone who's ever done that, you know that your reference data is not perfect. And so you might have measurement error in those reference data that you're not including. So you should say that you've got the sampling error just fine, but maybe color this one and say, I'm not considering measurement error in my uncertainty, for example. So that's the notion. I think I'm going to stop. I had my thing as an example, but I encourage you to look at the paper, argue about it. That's fine. We are, it'll never end. But I really do think that as developers of stuff, we should be endeavoring to try and communicate somehow what that we give. I think I'll stop there.
Yes.
Did I hear somebody say something? Sorry, was there a clarification? Oh,
Paper.
you're just gonna, I guess, the ERL, maybe I can,
It's right down there.
no, that's a different paper.
That's another
Yeah.
one. Ah, okay.
Yeah. Yeah, it's, yeah, okay.
Lessons from something carbon
Yes, characterizing
Okay.
and communicating uncertainty lessons from the NASA carbon monitoring system, something like that in environmental research
There's
labs.
only one paper of its kind.
Okay, thank you, I'm done,
okay.
thank you. Yes,
Since-
we muddled through that, that was
Yeah.
okay.
Chad, is it okay if we'll take one or two burning questions now because Chad's going to dive into some heavy stuff. Sorry. Unlike the previous presentation. Any burning questions? Either to Javier or to Robert.
So, to Robert, how would you recommend, so context, I'm trying to use your framework in the supplementary information of a forthcoming biomass map paper. Do you recommend that, how do we actually use that framework in the communication? Do you think that we should all just use that figure and augment it? Should we just reference it in the discussion? Just how do we implement the communication of uncertainty?
Right. So the vision that we had was that we could actually use that figure. As you're saying this, I'm realizing, I don't know if we actually have it as a graphic available for people anywhere. That'd be a good thing. But yeah, why not just use that? It's a simple thing, it's already there. But the other piece, which I didn't belabor here, but which we do talk about in the paper, is that if you color it in the way you think it should be colored in, there should be a narrative that goes with that, right? It's a metadata kind of thing, right? This goes along with your data in addition to the design of the sample or the pixel size or whatever those things that we always put in there. If we added this in, we should have that, and then we should say, I colored this box this way, or I didn't, because of X, so that you are explicit about you're communicating why you did that. So somebody else can look at your paper and they can be like, that's stupid, you should have done it differently. That's fine, that's science, right? But you're trying to narrate what the different choices are that you have on the graphic. Okay.
Right, thanks.
Now I'm really.
We're going to have to move on because we're 10 minutes late now. But go.
All right, hello everyone. I'm going to try to catch us up. So hopefully we can fly through this, and I'll get to a figure here about halfway through the original presentation, and then we'll just kind of hang out there and talk for a little bit about the geostatistical model-based estimator, and then and then I actually compare this to a design-based estimator and a model-assisted estimator. We can kind of compare how these three different approaches work, and how I'm trying to estimate forest biomass or forest carbon using these particular methods. So just to get us on the same page, eventually a slide on traditional, what I'm terming traditional forest inventory is coming up. Just to get us all thinking the same here. So in traditional forest inventory, we're thinking about using design-based estimators to try to estimate, for instance, forest biomass or carbon here in our context. So you go through and you select some field plot locations for your area of interest. You measure the amount of carbon on each of those plots, and then you can use a design-based estimator to estimate carbon for the project area. And then you can also estimate a standard error. So there's great advantages to this sort of design-based approach to estimation. These estimators are guaranteed to be unbiased, and we really appreciate that. And also the error is easy to estimate and interpret based on the sampling design that you use to select your plot locations. So some disadvantage, one major disadvantage though is that it is expensive to collect the field plot data. Usually we need quite large amounts of field plot data to be able to get estimates that give us result with acceptable levels of precision. So what we would like to do is be able to figure out a way to incorporate remote sensing data in some way to be able to increase the precision of our estimates without having to put in additional plot data. So we could use LiDAR data, LiDAR metrics, which are related to, which give us measurements of essentially of forest height, and we can use those inside different types of estimators. There's also optical remote sensing data, like from Landsat or Sentinel-2, but then also we can bring in above ground biomass maps that are publicly available, such as ESA's CCI biomass map or the JEDI biomass map. These are all free to the user to be able to download and use and potentially implement and use to help improve our estimates of biomass on the ground. So the trick is trying to figure out an appropriate estimator to be able to go in and be able to link this to the NFI data you might have in your country, and then be able to generate an estimate and be able to get that uncertainty. So we can look at different types of model-assisted estimators, which exist in the design-based paradigm of statistical inference, where there's an assisting model that's used that relates the remote sensing data to the field observations, and then we can use these model-assisted estimators to get at our estimate for the area and also standard error. And then we can also move over into the model-based realm of statistical inference, where we can essentially fit very similar models that we would actually fit within the model-assisted approach, but we're relying on distributional assumptions we make about the model we're using to be able to get at uncertainty in that way. And here's math, but I'm going to go really fast, so don't worry. So this is a generalized regression estimator, which is just an example of a model-assisted estimator that we can use. It essentially uses a basic linear regression model to relate the remote sensing data, which is that fun little X there, to my observations of biomass or carbon. So this is the NFI plot data. So we can get an estimate of biomass for the area, and then we can use a variance estimator to get at the uncertainty. In contrast to that, we can use what I'm going to show you what's called a geostatistical model-based estimator. So this is it's essentially, it uses a very similar model to the model-assisted approach, except that we have to be explicit about modeling spatial autocorrelation in our residuals, because to return us to the assumptions of the model. So we relax the assumptions of the model to be able to accommodate the fact that our residuals probably won't be independent and identically distributed. So that's that. So we're looking at three different estimators here. So we have a geostatistical model, this generalized regression estimator, and then we're going to compare, in our case study here, we're going to compare that to a design-based estimator, and we're going to see how they perform together using the same data sets. So we don't really have to get too much into what this map is, other than this is a map of biomass for the state of Oregon. So the larger area there is Oregon, and then we have counties inside the state of Oregon, which kind of exist as small areas where we can try to make estimates in there too. So this is the variable that we're going to put into the model-assisted estimator and the geostatistical model-based estimator. And there's some jargon about how the map was made. The most important thing to how this map was made is that the NFI data was not used to produce this map. I'm going to skip over that, but that's essentially we have National Forest inventory data for this area. There's 700 to 900 plots that were collected every year that we're going to use to be able to fit this data. So we're going to look at what's also called what I'm terming a direct estimator, which is essentially just taking the mean of the pixel values and then just deciding that that would be a good estimate of biomass. And then we'll look at the design-based, model-assisted, and geostat estimator. All right, here's the figure I wanted to get to, just to kind of be able to talk about how we try to compare them. So we had data for 2001 all the way to 2016. So we're making an estimate of above ground biomass density for each one of these years. So in 2001, you can see that the green dot here, this is my design-based estimate, and then I have a 95% confidence interval for that estimate. And then with the orange dot here, this is the model-assisted estimator, so that Greg estimator I showed, and then we have a 95% confidence interval for that. And then the GMB there, which is the geostatistical model, gives us an estimate, and we have a confidence interval for that. And then this pink dot way up here is the direct estimator. So we can see right off the bat that this map is very much over predicting biomass in general. But what's nice to see is that we do have the confidence intervals for the model assisted and well, especially here for the model assisted estimator, we are getting a little bit more confident in what our estimate is based on just using the field plot data alone. So this is reflecting how this map is actually helping improve our estimation of biomass in the area, but it's not substantial, is what I would argue, at least at the state level. So this is trying to get an estimate for the entire state, which we have 700 to 900 plots in each one of these years. So there's what I would argue is a sufficient amount of field data that we're not really getting any increased benefit from using additional remote sensing variables to try to improve the estimate at that scale. But if we go down to try to estimate for subregions, so this is Klamath County, so it's highlighted in red. So this is the particular county we're trying to get estimates for now. So we can start to see that we do get some more improvement, especially in the model-assisted estimator, when we start dropping our field plot sample sizes down a little bit. And then we can go to a smaller county. So now we're getting into counties where we only have 15 to 20 plots. And this is where we start seeing the geostatistical model start to show improvement over top of the model-assisted or design-based estimates. So this geostatistical model is the way it's structured. It's able to borrow strength from the relationship from predictions outside of the county to help inform what's going on inside of the county. And that's where we're starting to see that improvement. And then we can go down really, really small here. So now we're talking about a county that only has 5 to 8 plots in it in a particular year. And we do see quite a bit of benefit when we move over into the geostatistical model. One more figure. So on the vertical axis here, you see the 95% uncertainty interval width. So that's just the top of the confidence interval minus the bottom of the confidence interval. So essentially we can see that with the green dots here, so these are the design-based estimates this is for a particular county that had 5 plots in it in that particular year. So we see the uncertainty width is quite high for the design-based estimate. And you can see that they're quite a bit lower for the geostatistical model. So this is my sample size along the x-axis here. You can see when we get into counties that have 60 or more plots within them, we see that these estimates are performing pretty similarly. But then when we start to get to counties where we have quite a bit fewer plots, we can see that geostatistical model starts to show its benefits. So with that, I am going to stop, and I'm happy to take questions whenever Neha tells me I can.
maybe I'll show the two. Maybe we'll show the two, yeah, the two country cases, and then we'll take questions. Okay. Huh? You have a short question? Yeah, go ahead. Yeah.
The confidence interval you calculated with the standard error?
Yes.
What you're showing? Okay.
Yes, so in the design-based estimate and the model-assisted estimate, there's a variance estimate there's the variance estimator is what I use to get that confidence interval. Within the geostatistical model, it's done a little bit differently. That model is actually estimated using Bayesian inference, so I'm looking at posterior predictive distributions and these sorts of things. But at the end of the day, we can still produce a 95% uncertainty interval.
Standard error.
Yes. There's a different terminology when you switch between paradigms, but it's getting at the same thing.
Okay, I just want to quickly put two examples out here, bringing this back to reality. So we have a paper that's published using, it has Chad written all over it, using the geostatistical model for the country of Mexico, where two Earth observation products, the ESA-CCI biomass estimates and a JEDI Landsat-based height estimate, was thrown into a model that looks like that to be able to predict biomass where you don't have enough NFI plots. You just go to the next slide. Now, the advantage of using that model is that you're able to then kind of interpolate wherever you don't have plots and come up with predictions of biomass for any site, any national park, any state, any area that you're interested in. Once you're confident that the model can do the predictions, you can sort of populate it and fill it in with this. And the way the model is designed, because it accounts for spatial autocorrelation, the error from spatial autocorrelation, you're also able to get an uncertainty at the location of your predictions and for the entire area that you're predicting for. So I encourage you to look at the paper if you're interested, but then I just wanted to go to the next slide. This method was taken up by the Republic of Sudan, so we have the representative sitting here in the room, and they faced a situation similar to the case in Mexico, where their inventory was in progress, but they had gaps, mostly due to the war, inaccessible areas, but this is a situation that could arise in lack of funding and, unexpected incidences. Anyway, so for them, we used two auxiliary sources of data again. This is a JEDI estimated biomass and a forest probability map that was produced by FAO using Landsat and Alice pulsar imagery. So there's a whole bunch of satellite images gone in there. And the geostatistical model basically enables them to predict at the locations where they weren't able to go. So you can gap fill those NFI plots. This has now been submitted in the FRL report. It is still officially under review, but has undergone very good technical assessments. Two of them, I think, so it's doing well, and hopefully we should see it online as a final version in the next month or two. Okay, that's all. Yeah, any more questions? Sorry, I'll take a quick question before we move on to Monte Carlo. Yes? Sure.
Thank you. But I want just to highlight, when you are collecting data from the ground, you mix precision of the message you use with accuracy of the data that the human collect. Then when you build the model, you add this uncertainty to the accuracy of the model itself and bring remote sensing, then the issue of pixel, issue of changing from small to big pixel. So I just want to know how collectively this propagated or how will be estimated. Thank you very much.
Sorry, I'm going to try to try to figure this out. So you're talking about when we go out into the field and actually measure the trees, and then we use our allometric equations to figure out how much biomass is in the tree, and there's a lot of error at that level, right? So the approaches that I showed do not account for the error in the allometric equations. So we are assuming that whatever's measured at the plot is the truth. Typically when we are looking at using design-based estimation to be able to go in and get estimates for areas based off plot data, we're also not incorporating the allometric equation error in those estimates either, which is definitely something that we should be considering. It's a pretty difficult thing to be able to work with, and it's definitely not reflected in the approaches that I was showing here. Does that answer your question? At least a little bit? Yeah. No, that's I guess another level of uncertainty to try to dig down to, but that's is present in all three of the methods that I was showing.
But you could communicate it using the framework.
Yes, you could put a box that says this is important, but we're not reflected, that's not reflected in the confidence intervals we're showing here. Yep.
Like, we're going to have to hold because we're really late. Sorry, let's go through the Monte Carlo tool and then we'll see where we get, okay? We're 15 minutes late. Okay, so it's definitely not personal.
Okay, so I'm going to try to be quick, but I mean, along the process, we in FAO have been trying to support countries. I mean, not only we. I mean, the World Bank, different entities that have been trying to support countries. Now, with the new existing mechanisms, particularly under FCPF, and there are trees where it is requested that countries, in terms of the reporting, they use Monte Carlo, to do estimation. Now, the use of Monte Carlo is a bit of a big mystery in general for many countries, and they're all very interested in it. And so far, until now, basically, countries have been using Excel. And we will see an example later with Thomas from Ghana of the use of Excel for estimating Monte Carlo. Yeah, you can pass. But we now here are going to try to present a new tool. It's in first stages, so it's going to be in progress. But we hope that this tool will greatly enhance the capacity of the country to report uncertainties under Monte Carlo. Again, we are in this situation where we are in the tool is only going to be using the gain loss approach. Typically, where countries are going to get some activity data, okay, with the respective uncertainties associated to the activity data. They're going to have their carbon stock change factors or emission factors with the respective uncertainties. They are going to have ways of calculating each other, sampling errors, etc. And then eventually you are going to try to combine these things to produce overall emissions with the respective uncertainties, which is eventually what you want out of Monte Carlo. When you add up all the possible errors and you come up with a final result with its respective final combined error. Yep. But then we're going to have, of course, we're going to have a baseline or a reference level. We're going to have a sort of results. Each of them with their respective uncertainties, and then we also have to somehow get one minus the other and obtain the actual emission reductions with the respective uncertainties. So there's a lot of steps that are very complicated. It seems very complicated along the process. Please. So in theory, a reminder: what countries should aim towards is to prevent bias, right? To increase precision, and then we know that there is a way that where we have to combine sources of error, in order at least to increase the precision. Can you go to the next one? Okay, and when it comes to the combination of sources of error, the IPCC guidelines, they are telling us that we can use, in principle, the analytical method, the traditional equations of error propagation, but we are also told that to be careful because these equations, when you have very complex systems, very complex calculations, when you have distributions that are far away from the normal distribution, when you have a lot of correlations between variables, when you start to combine things, one thing with another, you have to end up using sort of simulation technique that is the Monte Carlo method. So that's the context where we are at. Okay. So now, Sanders is talking already. Yeah, wait. Okay. So there is publicly available material. Okay. There are, for example, guidance notes from FCPF, on how to estimate Monte Carlo. There are tools, there are Excel tools that are very simple guidance for countries to start to proceed with Excel to build a whole Monte Carlo process of combining errors. And again, as I told you, this is what we have been doing with countries so far. But we are trying to go one step over that. I think. Just to remind you that before I go to the Excel tool, that we are going to have visit the webpage because we're having another webinar on uncertainties upcoming soon in November. Right? And the Excel tool now. Yeah, the Excel sheet. So we're going to have a tool that I'm going to show you later, the actual application, but it's very important to tell you that this tool is going to need a series of input data, and this input data, they're going to come with the form of an Excel template that the countries have to fill up with some guidance, but we need this Excel template in order to have some kind of harmonized situation, harmonized information that the tool can grab itself and use it. So harmonizing that all the countries have a minimum series of variables or parameters that they need to fill up. So the Excel tool is going to have different tabs and associated to some basic parameters that they are going to need to put. You can travel a little bit between tabs if you want. Okay, so here you have whether you are using a truncated probability and density function. We are trying to build at the same time as a tool, a series of a tutorial, a series of guidelines. But there is different information about the different pools that are going to be used by the country, the units, whether the units are in carbon or in CO2 of carbon already, the input units. We are going to have to provide information on the periods. For example, here there is a reference period, in this case 2005 to 2014, and then you have, in this case, three monitoring periods. This is the example of Ghana that Thomas is going to show later. And then you have information of all the transitions that you are going to have, the land use transitions. There is a particular way of writing the transitions, okay? So the tool can absorb it, and you are going to have information on for example, in this case, I think it's area for each land use transition in the country happening. I think it's the emission factors. The emission factors for each transition, okay? And then information on the distribution, etc., and then I think and then carbon stocks. Well, basically. Yeah, there is going to be a bit of information. This is the emission factors. This is the carbon stock, sorry. Information on carbon stocks, all right? We will come with the tutorial, but this is just to give you an idea of how does it look like, how it's going to look like, the template. But now the sort of exciting thing is to go into the tool that, can reload.
We have 1 minute or 2 minutes. Sorry. Unless everyone wants to stay 30 minutes longer later.
No, very quick. Okay, go to the tool, continue the tool. Okay, so right now we cannot share because we need a hosting place for the tool. Okay, so we cannot share right now the link, but it's going to be available online. The idea is that you go and browse, and then upload the. Sorry, I touched it's browse and do that. Okay, you go browse and you're going to select your template that you have filled up already with all the information. Okay, and then I'm not complete, and then run checks. So the first thing you're gonna upload the template, and then you're gonna run some checks. It's gonna be completed. You show data checks. You click there, and then it's gonna give you some information already regarding the template that you have. No, in this case, the system identified that you have 4 reporting periods. You have 48 land use transitions in your template, and you are dealing with 4 carbon pools. And it is checking like how harmonized is your template in terms of checking the column names, table sizes, etc., etc. And it's going to give you a preliminary information. Here, there has not been Monte Carlo at all yet. This is what you would get in terms of the mean when you calculate emissions without any error, without calculating any error. Just to have an idea, no? So you're going to have a reference period, and you're going to have 3 monitoring periods here with their emissions. No? And then you can also use the land use change matrix to see what is the sort of idea of the areas, the areas that you are dealing with. You can select that for each monitoring time, and then I think it's going to show you different tables just to have an idea of what are your land use transitions. Okay, that's it. And then now for the Monte Carlo, you have to run the simulations. Okay, so you click there, and then you go up a little bit. Did it work? I hope it worked. Go to results. Yeah, go to results. Let's see if okay, it's doing it now. It's getting information for the errors that you input in your template, of all the carbon extras that you inputted, all the land use transitions, etc., etc. And now it has run. Now you show the simulation results, and hopefully, And this is the kind of thing that you're going to get. First of all, very important for transparency, and this is very important for the VBBs, NICOA. For transparency, you are going to be able to get the results disaggregated. Even each simulation, because you are running 10,000 simulations in Monte Carlo, you are going to be able to download everything in Excel to share it. But then also you're going to have results, in this case for each of the monitoring periods. You're going to have arithmetic mean. In this case, arithmetic mean. You can also use the median. The thing is, this is the arithmetic mean, and this is the median. That is what you have to report. Uncertainty percentage, the confidence intervals, a sort of an idea, a visual idea of how the emissions are for each period and the range. And then you're going to have a histogram also of emissions. What you get, you can select a period in the histogram. You can select the reference period for each period. You can select there. You can select every one of the periods, and it's going to show you a different histogram. So this is for emission reduction details, and then for each, you can also select for each activity. Okay, you're going to have tables, emissions, and then you can select, in this case, deforestation or degradation. No? Here we are reporting deforestation or degradation, and then for each time period. And then you can play with it, and it's going to show you the histograms, etc. Thank you very much. I'm sorry.
Okay, so every presentation, particularly Javier's, is running with a bias of 15 minutes. Can I have a quick show of hands if you're okay to stay longer, because it's a shame to cut it short? Okay, so seems like most are okay to stay longer. Then let's take a few questions before we move to Thomas, if there are any. Nicola. A question? Yeah.
Just a quick one. When will the tool be available?
We are hoping to have the first version, because the tool needs further improvements. We still haven't done sensitivity analysis. We still haven't done elements of continuous growth. For example, you are calculating growth or the slow oxidation of solid organic carbon. It is not there yet, so we're working on it. But the first version, like, is going to be very much what I have shown you. We are hoping to get it within 1 month when we do the webinar that I told you about. That will be the launching. We hope to get it by then.
Yeah.
The first is are you going to distribute the Excel file also?
There is currently, when you go to the tool, you can, there is a like a example template. I haven't shown you, but besides this
Okay, you send me, I send you an email. It's easier, I guess it's easy.
Okay.
I don't get where I need to go. So.
Okay.
Now, the second is the question. Are you considering to use also a kind of approach that you use the tier 1, the error propagation, simple equation like a primer, and then you adjust it with the Monte Carlo analysis to constrain
But
Monte Carlo?
including on the
No,
tool?
this is in general for your R&D, and maybe then in the future you develop something.
Okay,
So to use the two systems in sequence, one constraining the second. So the first, like, you assume that really the uncertainty is small and uncorrelated.
Yeah.
And then the second, you don't assume that they are small and uncorrelated, but the second,
But then
so it's a kind of bias and approach then.
Right, but then ideally that would come in the test of a tool also, not necessarily.
I mean, a PCC in any case asks you to do both. When you go for Monte Carlo, PCC say, okay, but do also approach one just for a kind of QA/QC. But what I'm saying is something different than QA/QC, to use as a priori probability the PCC tier 1 and a posteriori probability the Monte Carlo.
Okay, let's discuss about it. But we can, I mean, that's a good idea. Yeah, but let's discuss about it, yeah.
We'll take one more if there's more on the tool. No? Okay, there we go. If you wait long enough.
Does the model consider error from the elementary equations as well? Just stating the previous question for the last presenter too.
In principle, if you have an error arithmetic equation, it's going to be, you are going to have to incorporate it in your template already. So the tool is not going to calculate for each tree the error that comes with it. So the tool either starts to build Monte Carlo from your forest type, your stratum, wherever you have. So you need to have had incorporated the model error, the arithmetic equation error already. When you report the error for your stratum or your forest type, that error has to be already in there. So the tool is not going to start from tree per tree, right? That's another thing that in theory, yes, you should do, but then it becomes way too cumbersome and way too slow. Maybe in the future, other solutions like that might come up, but it will be more complicated. So we are trying to reach a sort of intermediate level of complexity here. Thank you.
Okay, thanks, Javier. We'll move on to the last presentation. This one's by Thomas Gambra from Ghana, who will take us through Ghana's Monte Carlo approach for FCPF and our trees.
Thank you very much. I have negative minutes, and the caveat is that I should speak very fast.
Not anymore. Everyone wants to stay longer, so take your time. Take your time.
Okay, thank you very much. So if that is the future, and here is the present, and perhaps the yesterday, as it were. So next, please. We've transitioned from the FCPF, and we are now with the art trees, as it were. We've submitted 2 monitoring reports to the FCPF. We've just submitted our 3rd report and are taking validation verification that's currently ongoing for our 3rd report under the FCPF. Also going through a validation verification for the art trees, as it were. And in both cases, as it said, have you indicated early on, we are doing Monte Carlo simulations or analysis to quantify the uncertainties related to the activity data and the emission factors. Next. So this is the overview of Ghana's situation, as it were, and doing this and per the IPCC standard and per the Act requirement, the FCPF methodological framework, we believe that the MC simulation provides a solution to allowing each step in the uncertainty estimation process to be modeled right, so that you can come up with one estimate of uncertainty. Next. This is the situation of Ghana. It's quite a complex one. We are doing for different vegetation zones here. So we have the activity data for the different vegetation zones. There are about 8 or 9 of them, as it were. And in each vegetation zone, we have what we call the closed forest and the open forest. Depending on the parameter, the closed forest is from 69% canopy closure upwards, and below 69 and 15% is for the open forest. So for each one, the activity data sampling uncertainty was considered by estimating the mean area change from the standard error from the systematic sampling of the land use. And we have that for each vegetation zone. We had the emission factors being calculated as well, and we needed to come up with the uncertainty predictions around that. So we used the means and the standard error in estimating separately for each forest stratum and separately for the carbon pool. So we had basically for the above ground, below ground, we have for soils, litter, and dead wood, as it were. Next. And we use the Monte Carlo, that's the older or the yesterday version. We have in Excel tool, we have, these are the parameters we use. There are there are 3 main Excel sheets that we worked with. The first one is the input parameters and assumptions. And here we have the parameters that we included in the model. We use the general factors, the biomass measurements, and we have the values that change for each period deforestation. So we had our reference period being 2005 to 2014, and here we are just using the first 2 monitoring reports. The first monitoring report was for 2019, and we have the second monitoring report for 2020 and 2021. We consider the removal factors, the removal from planting, that's for the 3 years, the emission factors for degradation, and the value change for each period, that's degradation for the reference period and also for the monitoring periods, as it were. Next. Now, in the Excel tool, we have one sheet that's the sources of uncertainty. In here, we have the monitoring period 1. These are aligning the parameters and the probability functions that we used. So you recall that these are the ratio of molecular weights, the carbon fraction, the above ground, have the below ground for the closed forest and also for the open forest. In Ghana's situation, the number of samples that we collected for the open forest was just too small, so we combined all the open forest for the various ecological zones. That's why I have one open forest in each of for the above ground and the below ground, as it were. We have for deadwood also as well, and we have for litter. But this is what we captured for the purpose of this presentation. Next. We also have, these are the outputs from the Monte Carlo and the simulated values. So in the Excel sheet, we have the second sheet is the simulated values, and this is how we went about it. You see the general factors, we consider the general factors, the biomass measurement, again, for all of the various ecological zones as we have in Ghana, and also for the various pools as we have also as well. And we had up to 16,000 simulations to work with for this particular exercise. Next, please. So in the Monte Carlo, the MC tab, so there are 3 Excel sheets. This is the MC tab. We highlighted the uncertainty reference level, and it's a 90% confidence, and you can see that for each year in there. And here we had the combined for the monitoring period 2020-2021. This is in line with the FCPF net framework, where you needed to combine the monitoring year. So we can have for each monitoring year, and you can have for the combined also as well. Next. Once again, we're able to also come up with the sensitivity analysis for the uncertainty calculations that we do. Next, please. And here, for instance, you can assign, maybe for deforestation, you can say that overall deforestation accounts for about 47.5 of the overall uncertainty. And whilst in terms of the general sources of the uncertainty, accounting for the activity data, you have, you can also account here. That's the 47.5 as it was. So this Excel tool is good. It helps you to come up with the key data you can assign. You can do that for degradation as well. You can do that for the various parameters as you want. And you can undertake the sensitivity analysis for this Excel tool. Next. So this is the last slide. Having gone through this process, we've tried to come up with the practical benefits of the Excel tool. And one, it allows for, it's traceable and allows for high level of transparency. In that, we are going to submit it to the VVBs, and they're able to go through the process as it were, and it can be adapted to country-specific approaches for data collection, can be accessed by anyone with that specific software expertise, because this is a market-based tool, and you are going to send it for verification at the end of the day, and it's easily traceable. But the key challenge is that the workbooks can be hard to understand and follow for anybody, but their developers, it's easy to make mistakes due to the large amount of inputs. This is just for Ghana. We have 300 lines as it were, and sometimes it takes a very long time, especially for the computation, for the sensitivity analysis, and interoperability of different Excel versions. So for instance, if you have Excel 365 and have the normal Excel, sometimes when you send it to someone, the values comes as XXX and all that. So these are some of the challenges as it were, and perhaps it's worth thinking through having this future as Javier presented. But for me, key thing is that the theoretical basis needs to be well developed and well understood. So this is the today of what we have, and we look forward to working with the FAO on the future as he presented. But primarily it's the theoretical basis for the tool that we need to work on and make sure that it's sound enough and mimics what countries are looking up to. Thank you very much.
Okay, I'd like to open the floor to questions to any of the speakers.
There's another speaker
Robert.
Thank you. This was a great set of talks. I really liked seeing a lot of the practical stuff too. So Javier, I love that tool demo, and congrats on pulling off a live demo in a session with a screen that was funky. So that was impressively done. Simple question, where was that tool running? It's running online somewhere when you were doing the demo? It's a website that you're launching a month from now, is that right?
Well, it is a Shiny app.
It's a Shiny app, okay.
Right now it's hosted in our developer, Gael Sola, Shiny app account. So that's what we need to move it.
Got you. Okay. Yeah. So it's going to have some permanent web address somewhere that has the compute power for everyone to run it.
I don't know.
No
Lauri,
problem.
you want to?
Yeah, we have a sign up.
So we have a sign up account, we can put it there running. This is now on the private account.
Yeah, sorry, Lauri Pesa is one of our colleagues in the field.
Perfect. Thank you. A follow-up question, is the code behind the Shiny app, is that going to be open as well?
I think we are hoping to, I think Gael has showed that it's going to be available in GitHub, basically.
If it's under open forest label, it has to be open.
Thank you, thank you.
Okay, any more questions on the general framework?
As the Excel tool that was demonstrated for our trees, so the Shiny app would also be accepted by some of these methodologies. What do you think about that?
That's a good question. Naiko, I would like to Naiko to say, maybe Muri, what do you think? What will you answer, Muri? I'm going to let Muri answer.
I mean, the VVBs should make all the efforts necessary to understand the methods and procedures of the countries. So if the country uses Shiny apps, they have to have people that can understand it. If we in Mozambique, we use our code for the Monte Carlo simulations, we share the scripts, share all the data, run them through how it works, and it's on them to understand it. Perhaps if it's a proprietary software, then maybe they have to actually sit with you and feel comfortable. That's my understanding from Mozambique. Thank you.
That is not going to be the case.
And Fiji does the same. So Fiji has their whole system in R with Monte Carlo, and they've been through the VBB process. It was very hard. I'm not joking, it took a long time. Because the VBB
sometimes they also lack the capacity.
They didn't have the capacity to assess the code. And so it took us a very long time. And also we had to continue to do more to show the full step out of everything. And to the point they were also asking us to implement it in Excel, which was really just not possible.
And that is really an issue. I mean, because we, I mean, for example, the issue with Sudan that you were mentioning is in R, and we face the situation with the BBBs have problems to evaluate these things. So next time you have to do something like that for your statistical approach in Excel.
It's impossible. It's analytically impossible. No, but yeah, we did go through hours of coding and line by line through the code, and it really takes that amount of commitment to explain the method. So, yeah.
Thank you, Neha, and thank you for all presenters. This is very interesting session. My question to Daniel, you mentioned about degradation other than the estimation of emission and removal.
Come again.
You mentioned something about the degradation. Are you estimating the degradation within the Monte Carlo tool other than the emission and removal? Thank you.
Yeah, so we considered deforestation, degradation, and removals. Degradation, as I indicated early on, we have remits within which we have the closed forest and the open forest. So for instance, we're able to estimate within the canopy cover, that's the canopy percentages. So within the closed forest, if the initial percentage were say 70 and it drops to say 65, that is still within the closed forest bracket, but it's a sort of degradation, and we are able to come up with the difference. So we come up with the average for all the closed forest, and we use that factor to come up with how the degradation for the emissions around the degradation. Similar approach is used for the open forest one. That's between the 15% and the 69%. So if it were 69 and forced to say 50, is the percentage change in there. Still an open forest, and we have the average also around that, and we use the factor that of the average to now reduce the emissions within that particular bracket. So that's how we came up with those figures. Yeah, I'll be happy to discuss more with you also as well.
Sandra?
Mine is a comment more than a question. The comment is the following. For deforestation, bisogna solo the calculation. For deforestation, when you use the average stock per hectare, no? The biomass, you have a level of precision calculated with your standard error, which is fine. But then when you go for deforestation, you don't use, your population is not the entire population that represent that value, is a subset, unknown. No, you don't have the measure of where the deforestation occurred. So if you apply that average value, is the variability of that value the source of error, not its precision. Because when you just have, let's assume you have the value is 100 with a range between 20 and 150. When there is deforestation, you apply the 100. But the deforestation may have occurred on the 20 or the 150. So that is the source of error. So that is the standard deviation that you need to propagate. And indeed, when you use an IPCC default factor, you shall always use the standard deviation, because our factors are calculated for populations that are bigger than your forest inventory. Sorry, forest inventory, your greenhouse gas inventory. They are regional, while you apply at the national level or the regional level. So you apply to a subset of the population for which that has been calculated. In this case, the variability became a source of, your main source of errors to propagate.
No.
Okay,
Sometimes it's an order of magnitude of difference.
okay, we talk later about that. Yeah. Close, yeah.
Okay, it seems like we might actually have to close at 5. So hold your questions and find them in coffee or lunch or dinner at the gala today. I'll hand over back to Javier because he has a few closing remarks with GFOI and uncertainties.
Just the few closing remarks is, as you can see within the GFOI, the people that are associated somehow with GFOI, within the topic of uncertainties that Chad and I are sort of leading, we are trying to still provide support. We will continue providing support. We are making new plans for what is coming or what is needed, and that's why we will need your inputs on whatever is needed. So we are open to your any kind of input. If you don't have my email, I can give it to you. I can give you my card, just in case for those of you who don't know me. And we are happy to keep supporting you as much as possible. So thank you very much.
Thank you. Yeah. A round of applause for the speakers again. Thank you for being an engaging audience. And yes, I encourage the communication to continue. All right. Have a nice evening.
Thank you.